I'm Gao Huang from Cornell University. The paper I'm presenting is densely connected convolutional networks, and this paper was jointly done with Zhuang Liu, Lawrence van der Marten, and Kilian Weinberger. We are fortunate to win the Best Paper Award this year. So this paper is on architectural design for convolutional networks. So convolutional was proposed about 30 years ago, and there are many changes being made to the architecture, which makes it more and more powerful. And 2 years ago, the basic architecture almost remained unchanged. Like as shown in this picture, each layer receives input from its previous layer and generates features for the layer right after it. 2 years ago, the deep residual network was proposed. So it introduces the identity connections to bypass signals across layers, and this greatly promotes gradient propagation in the network. And Resident has achieved unprecedentedly well results on many challenging computer vision tasks. In this paper, we propose a new connectivity pattern, which is called dense connectivity. The idea is quite simple. In this network, we connect every 2 layers in the network. So each layer receives signals from all its preceding layers, and the input is combined by channel-wise concatenation, which I will talk about in detail later. And in this network, as each layer has direct access to its preceding layers, so there's low information bottleneck in the network. So actually, we can make each layer much thinner and obtaining a much compact model. This gives high computational efficiency and parameter efficiency. And each layer generates K feature maps, and we call K growth rate here, and K is generally quite small. Now let's take a look at how the features are generated and used in the dense net. We have the original input x0, and we pass it through the first layer, which corresponds to a nonlinear transformation h1, and we obtain the feature x1. Now we concatenate x0 and x1 and use the second layer to generate the output for layer 2. And we concatenate the features obtained so far and use the third layer to obtain new features. And we keep doing this until the end of the network. And for each of the nonlinear transformations, it corresponds to a spectralization layer followed by a rectified linear units layer and a convolution layer with filter size 3 by 3. As you may have noticed, as we are keeping concatenating features in the network, the input to deeper layers will become very wide, and this may introduce too much computation for deeper layers. To address this problem, we found using a relatively cheaper convolution with filter size 1 by 1 to first reduce the dimension of channels to 4K could greatly improve the parameter efficiency and also computational efficiency. And here is the full picture of a dense net. As in a normal convnet, we have pooling layers or convolution layers to perform downsampling on the feature maps, and this makes the concatenation operation unviable. So to address this problem, we simply split the network into multiple dense blocks, and within each block, the feature map have the same size, so they can be easily concatenated. So you may wonder, we already have the amazing dense ResNet architecture, why we bother to use another network architecture. So here we summarize several prominent advantages of DenseNet. The first clear advantage is in a DenseNet, the error signal can be easily propagated to earlier layers more directly. So this is a kind of implicit deep supervision, as earlier layers can get more direct supervision from the final classification layer. And the second advantage here is DenseNet tend to have higher parameter and computation efficiency. For example, in each convolutional layer of a normal convnet, the number of parameters is proportional to C times C, where C is the layer width, or the number of channels produced at each layer. However, in the DenseNet, the number of parameters is proportional to L times K, where L is the layer index and the K is the growth rate. Usually, we have K much smaller than C, so the number of parameters in each layer of denseNet is usually much fewer than that in a normal ConvNet. Another advantage here is in a denseNet, the features to each layer is a concatenation of features from all preceding layers, and these tend to be more diversified and tend to have richer patterns. The third advantage is denseNet maintains low complexity features across the network. So in a standard ConvNet, the final classifier is built on top of the last convolutional layer, which produces most high-level features and also most complex features because it composes many nonlinear transformations. So in a denseNet, the classifier depends on features from with all complexity levels, and it uses both complex features and also simple features, and this tends to give more smooth decision boundaries, and this usually gives high generation performance. So this probably explains why denseNet works especially well when the training data is insufficient. Finally, let's take a look at how denseNet performs in practice. We first run denseNet on CVPR 10 dataset, which is a classification dataset with 10 classes. So here we first train, here the results of ResNet. The 110-layer ResNet gets 6.4% test error on this dataset, and 1,000-layer ResNet got 4.62% test error. Now we train a small denseNet with 100 layers and only 0.8 million parameters. We were able to get comparable performance as the 1,000-layer ResNet, but using about 1/10 of its number of parameters. And we train a larger denseNet. It gives significantly lower test error than previous state-of-the-art. The best results shown here is the previous state-of-the-art was at the time we submit our paper. So if we train the same models on the same dataset, but without using data augmentation, we can see that ResNet overfit to the training data severely. So both models get higher than 10% test error. However, denseNet is still able to get 5.9 and 5.2% test error without using any data augmentation. So on the CVPR 100 dataset, the trend is quite similar. And the small denseNet is able to get comparable performance as the much larger ResNet, and the larger denseNet gets state-of-the-art performance. So on the large-scale image-led classification dataset, denseNet is able to get similar performance as a ResNet, but using less than half the amount of parameters and about half amount of computation. So we recently trained a 264-layer denseNet. It got 20.27% top-line error on ImageNet. And finally, I'd like to talk about a REST network built on top of denseNet, which is called multi-scale denseNet. It is aimed for fast inference at the test time. The network learns multi-scale features at each layer, and it introduces dense connections at each scale. And most importantly, it introduces multiple classifiers attached to intermediate features. During inference, we first pass a test image to the first classifier, and we check the confidence level, which is the maximum softmax prediction. If the confidence is less than a pre-given threshold, we evaluate the second classifier. And until we keep evaluating until we get the confidence rather than the predefined threshold. And for the rest of features and the rest of classifiers, we can skip the computation. So during inference, we can exit easier images from earlier classifiers and only use expensive classifiers to evaluate hard examples. So this gives us 2.6% times faster inference than ResNet and about 1.3 times faster than denseNet. So if you're interested in using denseNet in your project, we have released our code and models on GitHub, and there are many third-party implementations. And we also recently wrote a technical report on how to implement DenseStat in a more memory-efficient way. And the technical report will be on archive maybe later today. And welcome to our poster. Thank you very much.